Hello everyone, and thank you for attending our talk where I will be presenting the preliminary results of our attempts to use concept languages as expert input for generalized planning. First, I would like to specify what sort of domain knowledge or expert input we are talking about. Consider this logistics example where a single package needs to be transported to its final destination by truck and by airplane. As humans, we can see that, at least in some sense, this state is less good than this state where there is a truck ready to take away the package. What we want experts to be able to express or have to express about these two states is what is interesting, what is different about these two states, not necessarily how to use it. So for instance, one thing that could be expressed is that there is a truck at a location where there is also a package, not the fact that this is good or bad or how to use it to solve the problem. Now that we know what sort of domain knowledge we're dealing with, let me show you the iterative process which we developed during this project. The first step of this iterative process is adding training instances. These are a set of problems, usually very small problems. And when we have these set of problems, our tool fully explores these state spaces, and then the result is a set of states which are considered the training instances. As a next step, the expert can add features that they think might be interesting about this domain. In our projects, we express these features in concept languages. Some of you might not be familiar with what concept languages are. Concept languages are a logic which consists of concepts which correspond to sets of objects. For instance, the concept package in this example consists of the set of exactly this package. And then there are roles which correspond to binary relations of objects. For instance, the at role associates objects with the position they are at. From these concepts and roles, which we get from the formal description of the domain, we can construct more complex concepts and roles, of which I will now give a few examples. In this example, we see the goal role at goal, which associates objects with the location they should be at in a goal state. This sub-expression corresponds to the set of objects for which their current location is the same as their goal location. And then, of course, the negation of that is all of the objects which are not currently at their goal location. Another example, we have the inverse of the at role, which associates locations with all of the objects that are at this location. We have the composition of at and its inverse, which associates objects with all the other objects which are at the same location. And we have the existential restriction here, which corresponds to all of the objects which are the same location as some truck. So what's important to note here is that these concepts can be thought of as sets of objects which have a certain property. And once we have these concepts and roles, we want to turn this into a natural number. And for that, we use features. And one such feature is the cardinality feature. For instance, using the slightly more complex concepts that we defined earlier, we can now define the number of packages at the wrong location with a truck. And in this state, this number would be 0. But in this state, this would be 1 because this package is not at its goal location here, and there is a truck at the same location. At this point, the work of the expert is done for now, and the information is handed over to the tool that we developed. The first step the tool takes is evaluating the features on the training instances. The next step, and the most important step, is to somehow turn these features into a heuristic. The heuristics we attempt to find are weighted sums of the features supplied by the expert. We can define some criteria by which to judge these heuristics and then compute the best weights for this criteria. And the way we did it is by solving mixed integer programs. We use two different variants. The first one attempts to approach a descending heuristic, which is good for satisficing planning because such a heuristic guides a standard greedy search directly to the goal. As a second approach, we try to locally approach the perfect heuristic, which we found complemented the earlier approach nicely in some way, which I will explain later. Then, when these weights are found, It is possible that we don't find a perfectly descending heuristic because the expert might not have provided enough or sufficiently informative features such that we have not fully reached a descending heuristic. In that case, the way we have implemented, there will be states which have a slack value associated with it. And these states are states that the current heuristic doesn't capture very well. If there are such states, then the tool will report these difficult states together with their successors. For instance, if we have the example from earlier, it is possible that this state cannot be differentiated from this state. And in that case, this is the output our tool would give. So as you can see, it describes the first state here and the second state here. It also tells you which operator is used to get from this state to this state. It shows you the evaluation of all features on this state and the evaluation or the value of the heuristic that was found on these states. And it also shows you the perfect heuristics. So this gives the expert a lot of hints on what to do to improve the set of features that they have applied. So then at that point, they can return to this step, add features, and repeat this loop until there are no more states with slack. And at that point, the expert needs to consider if the heuristic is good enough. And one way this could be done is by running experiments, testing the heuristic on all instances they have of a certain domain. If they are not satisfied with the heuristic, they can return to the first step and add more training instances. If they are satisfied, then they can stop. We implemented all of this and performed some experiments. Among other domains, we looked at the logistics domain, where we knew of a set of 12 features which together were informative enough to form a fully descending heuristic on the entire logistics domain. We added these features one by one and ran our tool, and we found that there is a general upward trend in the performance of the found heuristic with both approaches to finding the heuristic. We saw that the approach which attempts to mimic the perfect heuristic was more stable, justifying the inclusion of both approaches. But we also saw that adding features which are informative can actually worsen the heuristic. And we did some experiments on other domains as well. And there we saw that with some domains this worked very well, with other domains this did not work at all. And the performance of the heuristic actually only got worse the more features we added. One other thing we found is that our tool would have genuinely been very helpful to someone trying to independently discover this heuristic. Every step of the way, the tool provided outputs which was actionable and clear as to which aspects of the domain the heuristic was not yet covering, which would have significantly decreased the time, effort, and expertise required to discover this heuristic. So in conclusion, the preliminary results of our project are a system which allows an expert to specify and refine domain knowledge without having to know much about planning. And we have an approach to synthesize a heuristic from this knowledge, though both of these show mixed results depending on the domain it is used for. As future work, one way to improve our tool would be to automatically augment the feature set supplied by the expert. So we could take the concepts and roles supplied by the expert and apply some more operators to them, thereby expanding the set of features the tool can use to synthesize a heuristic. Secondly, we could attempt to use a different learning objective, since we saw that the learning objectives we are using might not be ideal. One candidate for this would be the goal distance rank correlation. We could also consider using a different learning method, because it is not necessarily the case that the learning objective that is causing the issues, and furthermore, mixed integer programs are quite slow. Finally, we could consider using a different input language. We used concept languages because it was shown to be promising and very intuitive for humans in previous work, where the features were automatically generated instead of handcrafted. But during this project, we noticed that handcrafting these features is a little bit clunky as a human, and perhaps something like a query language would be more appropriate. That's everything I have to say for now. Thank you for your attention, and the three of us will be available for questions if you have any.